Дима, ну,
Говорим по-английски, да?
Да. Сейчас, минуту. Dear colleagues, my name is Dmitry Simanchuk. I am a moderator of this section. 4 speakers will present their talks. All presentations are English. Not more than 12 minutes are given for every presentation. 2 minutes before the end of this time, I will inform you about this. After that, there will be 3 minutes for questions. During the presentation, the audience will be muted. After the presentation, you can unmute yourself and ask a question. In addition, question can be asked in the chat, and I will voice them. The same for the chat of YouTube, where the live broadcast goes. Меня зовут Дмитрий Шиманчук, я модератор этой секции. Будет представлен 4 доклада. Все доклады делаются на английском языке. На каждый доклад отводится не более 12 минут. За 2 минуты до окончания времени я сообщу об этом. На вопросы отводится 3 минуты. На время презентации я буду отключать микрофон всем зрителям. После презентации у вас появится возможность включить свой микрофон самостоятельно и задать вопрос. Кроме того, вопросы можно задавать в чате, я буду их озвучивать. Это же касается YouTube, где сейчас идет прямая трансляция. This section is chaired by me. And now the first report is construction of connection trajectories in the circular restricted body problem, represented by Shmerov Vasily. Please, Vasily.
Thank you. Dear colleagues, let I begin my report. The theme of my report is construction of connecting trajectories in the circular restricted three-body problem. Of course, this theme is enough big. Our report, me and my co-authors, in concrete areas of space, this investigation with respect to collinear or Lagrangian points of some of systems. Okay, in this investigation, we consider the problem of construction model of restricted three-body problem and with more simple problem model of Hill. In first, I want to show you the liberation points in some of system. The blue point is the Earth. L1 and L2 is partial solutions of restricted three-body problem, and it is with connection with some interesting space projects was realized by National Aerospace Agency and some projects, some projects of Roscosmos and other and China's and European projects. The interesting problem is transfer and maneuvering from the neighborhood of L1 to neighborhood of L2 and back It is a fact the apparatus Genedis flew between these areas of space in 2001. We see the practical importance of these investigations. In this slide, the equations, classical equations, one of variants of equations in the geocentric system of coordinates of circular three-body problem. This is classical formulas. May rewrite the equation in Hamiltonian form and transfer to a rotation coordinate of coordinates, system of coordinates. The formula 3 in Hamiltonian form and equations of motions in first order we see in view 4. Some interesting effect is the symmetry of trajectories with respect to x1 or x1 axis. In other words, these some trajectories x1, x2 in the plane of ecliptic. I want to add some words. This is important for understanding of these equations in first time. That x3, y3, the coordinates of space and we usually in simple case work with motion in ecliptic of plane, ecliptic movement of the Earth around the Sun. It is ecliptic plane. And ecliptic plane, there is some symmetry. Oh, this is interesting fact. We can check it in view 4. View 4. The idea of our investigation, that we use in the first stage, in Hill's model, I'll speak about it in nearest minute. What about idea? At the first stage, we constructed some trajectory in Hill's model and use some additional properties of symmetry, some additional properties with respect to restricted three-body problem. Okay, and our slide, we see the Hill's approximation or some another name, Hill's equations. This is not Hill equation, Hill's equations many times of motion of space vehicle in neighborhood of Earth. Then we take in account the views of Sun. In this case, we some additional solution. But before I show you the Hamiltonian, of equations 5. Equations 5. This is the approximation, some approximation, special approximation in simple words of Hamiltonian 3, Hamiltonian 6, some after working, after expanding of this part on small values, we get the Hamiltonian 6. And the interesting fact that liberation point L1 and L2 are symmetric in this model. In model of a restricted free body problem, this is not true. This is not true. L1 and L2 on different distance from the center of the Earth, and restricted free body problem. Okay, and some exercise on this model, the foundation of addition symmetric about the axis x2. Okay. For some understanding, I'll show you in next slide the plane x1, x2, the Earth in the center, L1, the coordinates of L1, minus 1, coordinates of L2. I speak all time about it. Okay, and this is symmetry not exist in more expanded model of restricted free body problem, and we use it. Some approach, some special approach, the construction of condition data with this formula, then x1 equals 0, and derivation on x2 0, 2. Some approach special, our choice for construction of initial data, and if we have this picture with respect to L2 on the right of symmetry, we show the symmetric graph with respect to achievement of equation of neighborhood of L1. L1 is here. I show you with mouse. Okay. And other we check it in more expanded model restricted free body problem. Our numerical experience we transfer to more global mathematical problem. Okay, this is connecting trajectory.
Vasily, 1 minute left.
Okay. Connecting trajectory in model, and the same with the same data in restricted free body problem. There's some with other initial data than in figures 1, but with same idea of construction of initial data. Okay, and the last figure, this is some other experiments, some other experiments for construction of kinetic trajectories between neighborhoods of collinear liberation points L2 and L1. Thank you.
Thank you.
I complete my report.
Thank you for interesting report. Dear colleague, we not have a few minutes to discuss it, but please ask your question. Okay, Vasily, thank you. And
Thank
now we go to the next report. The next report is construction a polynomial method in the state space for a nonlinear optimization control problem. It's represented by Zlobin Daniel. Please, Daniel.
Hello, I can start demonstration of the screen.
Vasily, could you please share it of your presentation? Daniel, please.
Hello, my name is Daniel Zlobin. The work was done jointly by Dmitry Shimanchuk. This work shows a method for taking into account phase constraints and control constraints in the direct construction of a quasi-optimal polynomial trajectory in the state space of a system of a special form which allows one to exclude control from tasks and build a trajectory directly in the state space. Let he be a vector characterizing the state of the system and U be a control. Consider a controlled system of differential equation of the following form. We will assume that for a fixed t, the function p is a polynomial, and using t, the coefficients of the polynomial are parameterized. The function phi is a linear transformation containing in the orthogonal group of some given non-singular quadratic form Q. And hereinafter we will use this notation. We set the trajectory and control limits as follows. The control constraint is given by a quadratic form. The trajectory must satisfy a stationary differential inclusion of degree n -1. For differential inclusion, the boundary differential inclusion is set. We restrict ourselves to the case when the set MT is the intersection of a set with an algebraic boundary and the convex set. For a given system with constraints, consider the problem of minimizing a given quality functional. Consider a quasi-approximation of the original problem, assuming that the trajectory system is a polynomial. To find the optimal trajectory, we exclude the control. To do this, we express the control from the differential equation using the inverse orthogonal transformation and substitute it into the quality functional and the quadratic form. After that, we get the problem in the state space. Since he is a polynomial of finite degree, this functional is a function of finite number of arguments. Let us transform the constraints on the trajectory of the system into constraints on the finite set of parameters that define the admissible trajectory. To do this, we first consider the boundary inclusion. It's known from the theory of interpolation that a polynomial of minimal degree satisfying boundary conditions is a Hermitian polynomial which in this case can be written as shown on the slide. Using the Hermite polynomial, we obtain a parameterization for a polynomial of arbitrary degree satisfying the boundary condition. For arbitrary parameters A, this polynomial satisfies the boundary inclusion. Now we need to find constraints on the vector coefficients A. It is very difficult to transfer the constraints from a polynomial trajectory to its coefficients. There are criteria that make it possible to determine the presence of roots of a polynomial on an interval. But even if the computational complexity is not taken into account, it is impossible to use this criteria together with gradient optimization methods. Therefore, we will transfer the constraints to the coefficients approximately, but in such way that the implementation guarantees the fulfillment of the original constraints. First, consider the inclusion in the set with algebraic boundary. This set is defined as the set of solution to the polynomial system of inequalities. It's necessary to obtain an approximation of the range of values for polynomials Z. We introduce the operator that maps a polynomial to a vector of its coefficients. Then any polynomial can be represented in the basis of Bernstein polynomials of an arbitrary sufficiently large degree k using the linear transformation lambda. Then used the following well-known properties of the Bernstein form. First, we can estimate the values of the polynomial on the unit interval using the Bernstein form coefficients. It is known that these estimates are asymptotically exact as the degree of the basis of the Bernstein polynomials Bernstein form increases. Then we can transfer the constraints from the trajectory to its parameterization. And these constraints on the parameters are asymptotically exact. For a vector-valued polynomial, we define matrix-valued operator. Thus, we have obtained condition for the coefficients of the polynomial. This inequality is coordinate-wise. Convex constraints can be approximated in a similar way. For the vector coefficients of the Bernstein form, it is known that the convex hull of the polynomial trajectory is included in the convex hull of the coefficients of the Bernstein form of a given trajectory. Since the set is convex, the trajectory is contained inside this set if and only if the convex hull of the trajectory is completely inside the set. Thus, we obtain the constraints on the parameterization. If set M, define it as you can see on the slide. Using this approach, we can write a nonlinear programming problem on the parameterization of a polynomial trajectory of a given degree, with a given degree of approximation of the constraints. The first group of constraints corresponds to polynomial trajectory constraints. And the second group corresponds to convex constraints. The third group ensures that the boundary conditions are met. For the numerical solution of the problem, one can use, for example, the method of the sequential quadratic programming. Let us consider the implementation of the method using the example of finding the time optimal trajectory for the landing of an unmanned aerial vehicle on a moving platform. It's required to land the UAV on a platform moving in a circle with a radius of 2 kilometers at a speed of 54 kilometers per hour at the moment of landing. The UAV speed must be co-directional with the platform speed and equal in magnitude to the specific landing speed. Let the following constraints be given. The task can be reduced to the following form with following constraints. This is a special case of the considered problem. Required to minimize landing time. Consider the implementation in MATLAB. The green lines indicate the trajectories that were consistently obtained while minimizing the landing time. And the bold black line indicates the found trajectory of landing on the platform moving in the circle. Thus, the problem of finding a quasi-optimal trajectory is approximated by the finite-dimensional nonlinear programming problem of the coefficients of a special type polynomial. An obvious addition of the method obtained is that there is no need to worry about the behavior of the trajectory between test points, because optimization is carried out according to coefficients restriction on which guarantee the admissibility of the trajectory. Also, parameterization using the Hermite polynomial ensures that the exact fulfillment of the boundary condition of the trajectory. The presented method is suitable for cases with non-convex constraints and allow us to separate the convex part. As it's not difficult to be convinced, this method is applicable to a more general type of a differential inclusion. If the following set is the intersection of a convex set and a set with algebraic boundary. So references. And thank you for your attention.
Thank you, Daniel, for your report. Dear colleagues, please ask your questions. We have a question in chat from Vasily Shmyrov. What is the D in power n, and what is the Q in power plus? Or also simple Q plus.
D power n is just this notation. And там еще в конце можете повторить?
Q plus.
Q plus?
What is the Q plus?
Is just a number upper bound.
Restriction.
Yes.
Okay. Okay.
Thank you. Thank you, Daniel. The next report is about controlled motion of spacecraft with a solar sail, represented by Nikolai Stepenko. Please, Nikolai.
Hello, my name is Nikolai Stepenko. I present a report about controlled motion of spacecraft with the solar sail. The many problems are possibilities of using the solar sail for spacecraft flight led to the emergence of various projects based on the approximation of the equation of motion for various orbits and parameters, the possibilities of controlling the motion in a given orbit are discussed. Light pressure hypothesis for the first time was expressed by Kepler to explain the deflection of the tiles of comets passing near the Sun. The principle of movement in space on the solar sail is based on the effects of light pressure discovered by Leibniz. To use power of light pressure on the surface of the special elements of spacecraft sail, this good reflection coefficient for interplanetary flight was proposed in 1924 by the Russian scientist Friedrich Sander. This book reflects the history of creation. If the solar sail is a metal and reflects most of the rays, then the force of light pressure will be directed almost normal to the plane of the sail. This is project Novicy. This is a variety model of sail. Let's consider the main variants of the problem of theoretical mechanics of space flight. The heliocentric motion of the spacecraft with a solar sail and the photographation the two-body problem when flying to the Sun, the planet, asteroid, or comet, are establishing special orbits of motion in the vicinity of the Sun given the pressure of solar radiation. The equation of dynamics can be written in the system of second-order equations, dividing the potential perturbation forces and the light pressure on the sail element for control. Here are some control methods in such environment. You can use Euler differential equation of motion of the apparatus in Kepler's oscillation element. Other models of equation can be applied. This way. Other model. Control of spacecraft orientation. For changes the slope of the spacecraft orbital plane with the help of the sail, you must send the reflected solar flux perpendicular to the initial plane. We get the ability to control the direction of the thrust vector by the sail tuning. This slide shows formation forces and flight pressure moment. The trajectory of the spacecraft in the presence of the tangential component of the force of flight pressure on the sail. On this slide. This slide shows rotary motion control related to selected axis. And this main part of the report in the inverse problems of dynamics. Considering the inverse problem of dynamics for finding forces along an or given motion of a spacecraft, we can find control acceleration that must release additional forces for moving along the desired trajectory. The motion equation of photographical file of the sun is follows. This vector A is the controlled acceleration. This fine. We are applying controlled acceleration in this equation. Then we consider the tail which is specially reflective from its both sides and then inclined to solar array by arbitrary angles, gamma 1 and gamma 2. This controlled acceleration is AX, AY, Z, and dimensional factor K. This slide shows relation shift for angles and time mesh. We considered three-dimensional curve, Vianney curve, this equation. Vianney curve is slightly flattened in vertical direction. Below we present the graph of gamma 1, gamma 2, and schedule for S over M. Let us pass the petals of the Vianney curve closer to the poles of the sun. Graph shows the orbit of the shift for the angle switching point. This is cardioid curve trajectory, and angle gamma 1 and time length. This is asteroid trajectory. And animation for helical trajectory. This spacecraft moving on this trajectory. This is bibliography. Examples of edition from the reference. Thank you. I complete my report.
Thank you for your report. Dear colleagues, please ask a question. In this case, I have a question. Could you please, what is the area of the cell present in the research. An example.
Yes.
When you
one atomic and
Nikolai, where are you?
одна астрономическая единица, 1/10.
It is distance, but I say about cell area. Площадь.
Area,
The size.
10 meters and over by power 2. Ну, десятки квадратных метров.
Any questions? Thank you. Any questions, please? Okay. Thank you for the report. The next report is boundary control of string vibration with given values of the deflection function at intermediate moment of time, represented by Bargisyan Vanya. But unfortunately, there is information that the speaker will be absent. But we have a video presentation of the report, and we will launch this video now.
Hello, dear colleagues. Because of the facts known to all of you, the presentation cannot be made in real-time mode. I wish all of you productive work. Now the presentation on the topic boundary control of string vibrations with given values of the deflection function at intermediate moments of time will be made for you. First, the setting of the problem will be presented. Then the problem will be reduced to a problem with zero boundary conditions. Next, the solution of the problem will be presented. Then example with computational experiment. In this slide, the problem setting is presented. Let the state of the distributed vibrating system, the deviations from the equilibrium state are described by the function Q. Database for this X and T. The wave equation presented in equation denoted by 1.1 with initial conditions 1.2 and boundary conditions 1.3. Where functions mu and nu are boundary controls. The boundary control problem of strict vibration is posed as follows. Reduction of the problem to problem with the zero boundary conditions. We seek for the solution of the equation 1.1 in the form of sum denoted by 2.1, where v is an unknown function satisfying equation 1.1 with the homogeneous boundary conditions denoted by 2.2, where boundary conditions presented in a formula denoted by 2.3. By virtue of initial, intermediate, and boundary conditions, respectively 1.2 and 1.3 and 1.5, the function v must satisfy the initial conditions denoted by 2.7 and intermediate conditions denoted by 2.8 and final conditions 2.9. From condition 2.2, it follows that following statements denoted by 2.10. From conditions 2.7, 2.8, and 2.9, taking into account 2.10, we can obtain the following compatibility conditions denoted by 2.11, 2.12, and 2.13. Thus, taking into account conditions from 2.11 to 2.14, the conditions from 2.7 to 2.9 are written as follows respectively. Thus, the boundary control problems of string vibration is reduced to control problem 2.5, 2.6 with boundary condition 2.2, which is formulated as follows. It is required to find the boundary controls mu and nu for the t and transferring the motion 2.5 with the boundary conditions 2.2 from the given initial state denoted by 2.14 from the intermediate states 2.15 to the final state 2.16. Here, the problem solution is present. The solution of the equation 2.5 is searched for in the following form denoted by 3.1. The functions functions are presented in the form of Fourier series and substituting their values together with function v into equations 2.5, 2.6 and into the conditions 2.14, 2.15, and 2.16, it is obtained that the following equations, where the condition 3.6 is true. The general solution of the equation 3.2 with initial conditions 3.3 and its derivatives with respect to time have the form of the equations denoted by 3.7. Now, taking into account the intermediate 3.4 and the final 3.5 conditions from 3.7, it is obtained that the functions f for each key must satisfy the relation denoted by 3.8, where the following conditions are true. To find the functions mu, the infinite integral relations 3.8 are obtained. In practice, based on the model method, some first enharmonics of elastic vibrations are selected, and then a control synthesis problem is solved using methods from the theory of control of finite dimensional systems. Following model method, for the first few harmonics, the following notations for block matrices are introduced. For the first few enharmonics, here and in what follows, the presence of n subscribed denotes the first few enharmonics. Taking into account 3.9 from 3.8, we have the following. For an arbitrary number of the first harmonics, the boundary control action mu satisfying the control action u satisfying the integral relation 3.10 is constructed in the form of equation 3.11, where H is a transposed matrix and F is a sum vector function, such as the following functions. In the next slide, example is presented. Let's consider the case when we have the following conditions. For simplicity, U boundary control function, let's construct when n is equal to 1. We will have this condition, and therefore we can obtain the followings. We denote by S1 minus 1 the following matrix, where this condition is true. From formula 3.11, it follows that the following equation. Finally, we can write an expression for the function in the form in this form. Here, the example with computational experiment is presented. Let's assume that T1 and T are the followings. And then taking into account this condition, we can obtain for S and S1 minus 1 the followings. And supposing for A and L the following values, we can get the following followings. In this slide, you can see the graph of the function u1. For the function u1 of t, the following estimation is obtained. The value of the deflection function q1 at the final moment of the first interval coincides with the value of the beginning of the second interval, and it has the following forms. In this graph, the functions q1 is presented with the solid line, and C0 presented with a dotted line. In this slide, comparison of Q1 and C1 is presented. The presentation is made by using this value. The deflection function and its derivative at the moment of time when t is equal to 6 have the following forms. Here is the graph of the function of q1 of x at 6, and derivative of function q1. Here presented bibliography, and thank you for attention.
Can you hear me? I think that in this case, if you have any question to Vanya Burgisyan, you can write and send a mail to him. And now we listened to all the report of this part of session. See you in the next session, which start at 15:15.
Окей.
Так, Василий, ты здесь?
Ще.
А ты, надеюсь, еще остаешься?
Мы в прямом эфире.
Да, да, конечно. В прямом. Но дело в том, что сейчас перерыв. Сейчас 15 минут перерыв.
Я сейчас вынужден буду, все-таки уехать с детьми. Вот.
Ну ладно, тогда я тоже помолчу.
Не зовите вы нас чудаками, не спешите нас осуждать. Так уже велось веками, что кому-то всегда рисковать. Так уже велось веками, что кому-то всегда рисковать. Вместо чьей-то известности громкой неизвестность свою предпочесть. Чтоб знали о нас наши потомки, что огонь в наших душах есть. Чтобы знали о нас наши потомки, что огонь в наших душах есть. Нет, не забыть нам никогда эти юные года, этих дней бесконечных нить. Чтоб тревоги унять, надымать и опять юность свою повторить. Чтоб тревоги унять, надымать и опять юность свою повторить. Словно давка свои сердца мы на ладонь положим земли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Мы счастливее очень многих, тех, кто призван творить, создавать. Мы проложим пути дороги, по которым не нам тосковать. Мы проложим пути дороги, по которым не нам тосковать. Словно давка свои сердца мы на ладонь положим земли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли.
Стучат колеса неустанно, неутомимый электрон везет желающих к фонтанам. Приветствовать тебя, Самсон, герой, прославленный навеки в сказаниях Библии Святой. Зачем мне упросили греки Геракла встретиться с тобой однажды в споре суетливом? Самсон проспорил свой заклад. Не захотел быть он несчастливым, не захотел попасть и в ад. Со слинной челюстью он вышел на торные в те дни пути, и 30 путников, я слышал, до дома не смогли дойти. А он, герой библейских песен, с лишенных жизни снял штаны и расплатился в споре честен. Видал ли Бог, но с вышины? Стоишь, вот теперь и пасть льву раздираешь, а он хрипит и бьет водой. Сковал тебя Господь, ты знаешь, чтобы мир не видел твой разбой. Герой, прославленный навеки, в сказаниях Библии святой. Зачем мне его простили греки? Геракл встретится с тобой.
Зовите вы нас чудаками, не спешите на нас осуждать. Так уже повелось веками, что кому-то всегда рисковать. Так уже повелось веками, что кому-то всегда рисковать. Вместо чьей-то известности громкой неизвестность свою предпочесть. Чтобы знали о нас наши потомки, что огонь в наших душах есть. Чтобы знали о нас наши потомки, что огонь в наших душах есть.
Нет, не забыть нам никогда эти юные года, этих дней бесконечных нить.
Чтоб тревоги унять, на примате опять юность свою повторить. Чтоб тревоги унять, на примате опять юность свою повторить. Словно давка свои сердца мы на ладонь положим земли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Мы счастливее очень многих, тех, кто призван творить, создавать. Мы проложим пути дороги, по которым не нам тосковать. Мы проложим пути дороги, по которым не нам тосковать. Словно дамка свои сердца мы на ладонь положим земли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли. Что по трассам, рассчитанным нами, мчались к новым мирам корабли.
Крылом в окно стучится вьюга, как будто просится к теплу. Крылом и клювом бьется птица за заиндевевшее окно. Стекло не хочет приоткрыться, ведь бессердечное оно. А я дверей не закрываю, замков не вешаю стальных. Друзей с любовью принимаю, с отрадой в сердце остальных. А я дверей не закрываю, замков не вешаю стальных. Даже коршун бьет в полете трепетную птицу, мой кров всегда ее спасет, от смерти лютой даст укрыться. И если молния сверкнет, стрела над головой просвищет. Ее не страшен мне полет, пущу ее в жилище. А я дверей не закрываю, замков не вешаю стальных. Друзей с любовью принимаю, с отрадой в сердце остальных. А я дверей не закрываю, замков не вешаю стальных. Друзей с любовью принимаю, с отрадой в сердце остальных. А я дверей не закрываю, замков не вешаю стальных.
And now we start next session. My name is Dmitry Simanchuk. I am moderator of this section. Four speakers will be present their talks. All presentations are in English. Not more than 12 minutes are given for every presentation. 2 minutes before the end of this time, I will inform you about this. After that, the will be 3 minutes for questions. During the presentation, the audience will be muted. After the presentation, you can unmute yourself and ask questions. In addition, questions can be asked in the chat and I will voice them. The same for the chat of YouTube, where the live broadcast goes. Меня зовут Дмитрий Шиманчук, я модератор этой секции. Будет представлено 4 доклада. Все доклады делаются на английском языке. На каждый доклад отводится не более 12 минут. За 2 минуты до окончания времени сообщу об этом. На вопросы отводится 3 минуты. На время презентации я буду отключать микрофоны всем зрителям. После презентации у вас появится возможность включить свои микрофоны самостоятельно, задать вопрос. Кроме того, вопросы можно задать в чате, я буду их озвучивать. Это же касается чата YouTube, где сейчас идет прямая трансляция. The session is chaired by me. The next report is vibration control of a known homogeneous circular thing plane. This report will be given by Grigory Vasilyev. Please, Grigory.
Thank you. Can you hear me?
Yes.
Okay. In the research I'm going to present, we study free transverse vibrations of an inhomogeneous circle thin plate. If the plate is inhomogeneous, the problem becomes significantly more difficult, even for the case when the plate parameters depend only on the radial coordinate. The absence of an analytical solution of the equation of vibration in this case makes necessary its numerical solution. For this, a numerous articles, some of which are included in the references at the end of this presentation, various numerical methods were used. For example, the Rayleigh-Ritz method, the differential quadrature method, the Frobenius method, and other methods. The aim of our study is to obtain the vibrational frequencies of inhomogeneous plates in the form of power series and small perturbation parameter using the asymptotic method. In our study, the thickness or Young modulus of the plate are functions of the radial coordinate. Thus, the transverse vibrations of an inhomogeneous thin plate is described by this equation, which after separation of variables and transition to the polar coordinate system take the form of equation 2, where the coefficients of the linear differential operator L are equation 3. Let us pass in equation 2 to the dimensionless variables with the tilde symbol, which is further omitted. For a plate with constant dimensionless parameters, the cylindrical stiffness and thickness are equal to unity. Then we use the perturbation method. We represent all variables and parameters in the form of power series in the small parameter epsilon. After substituting and equating the coefficients with equal powers of epsilon, we get a sequence of boundary value problems. Its existence condition is the orthogonality of the right-hand sides of equations to the solution of the unperturbed problem, the problem for homogeneous plate. In the general case, the condition is as follows, from where we get formulas for the terms in the expansion of frequency. The solution for the case of a homogeneous plate is linear combination of Bessel functions. From the boundary condition, we obtain the frequency equation 7 and 8. And the form of vibration is here. In this work, linear, quadratic, and exponential perturbation were analyzed. Cases when the mass or average stiffness of the plate doesn't change were also considered. The plate with the fixed edge and with simply supported edge were discussed. It is in this work we find only the first term and the expansion for frequency. We will consider the low part of the spectrum with such vibration modes. Presented here are images from COMSOL. In the picture on the left, you can see the top view of the plates, from which the wave numbers of the corresponding vibration mode are easily determined. The picture on the right is a side view, and not the deflection itself is shown by this modulus. To obtain the first frequency approximation, you need to find operators f11 and f12, which are given by formulas, from where we get the formula for the first term in the frequency expansion. To the table shows the results of asymptotic calculations. The asymptotic results are compared with the numerical results obtained with the help of finite element package COMSOL. Hereinafter, solid lines correspond to the frequency calculated asymptotically, and dotted lines numerically with COMSOL. As the thickness increases, both stiffness and mass increase, but the effect of stiffness is more significant since it depends on the cube of the thickness. As a result, frequencies increase monotonously with epsilon. It can also be noted that for small values of epsilon, the asymptotic values are close to exact ones, and the decrease in frequency with a significant decrease in thickness of the plate toward the edge is much faster than linearly. While maintaining the mass of the plate, the lower frequencies are weakly dependent on changes in thickness. Under different boundary conditions, the difference is small, but is simply supported with simply supported edges. The fundamental frequencies decreases with increased epsilon, and the fixed edges it increases. With increasing wave numbers m and n, the dependence of frequencies on changes in thickness increases, being close to linear, and the order of frequencies is violated. With monotonic increase of Young's modulus, frequencies increase predictably. With a significant decrease in epsilon, the decrease in frequencies is sharply accelerated, which is associated with a low bending stiffness of the plate. The choice of boundary condition has little effect on the behavior of frequencies when epsilon is changed. Here, frequencies are plotted for the case when the stiffness changes linearly, but the average value of Young modulus is conserved. As you see, the effect of perturbation parameter epsilon frequencies is close to linear even for epsilon values close to 1, and the lower frequencies are almost constant. Also, two inequalities fulfilled. The dependence of lambda 1 on m and n is of research interest. Since the quality of the frequency behavior doesn't depend on the considered boundary condition, further results are presented only for a place to the fixed edge. The effect of thickness variation on frequencies in the quadratic case is significantly larger than in a linear case. In this and the following tables, numerical and asymptotic values of the frequencies and their comparison with the results of other authors are given. The error of the asymptotic result doesn't exceed 1%, even for values of perturbation parameter close to 1. In the left picture, you see that the dependence of the frequencies on epsilon when the stiffness changes quadratically is similar to the case when the stiffness changes linearly, but the values of the first corrections to the frequencies for the linear case are larger. It can be seen in the table on the next slide. The plot to the right corresponds to the case when the average plate stiffness remains constant. We can see that the dependence of the frequencies on the perturbation parameters is non-monotonic, in particular the axisymmetric frequencies attain maximums at epsilon close to 0 Q. In the presented data, you can see a pattern. For a fixed m and increasing n and vice versa, the value of lambda 1 increases. Since such an exponential function is approximated by a linear one, then for small values for epsilon, a linear perturbation should be expected to give a good approximation for the frequencies of a plate with exponential change in thickness. Table 2 showed the numerical and asymptotic values of frequencies and their comparison with the results of other authors. Changing the stiffness according to the exponential law is of practical interest in studying vibration of biomechanical structures. For example, a mesh-like structure called the lamina cribrosa in the eye, the stiffness of which is approximated by exponential function, which decreases from the center. Since for small values of epsilon this function and its linear expansion are closed, it is interesting to compare the results of numerical calculation of frequencies for a nonlinear exponential perturbation and asymptotic for a linear perturbation. In the figure, we see good agreement of numerical points and asymptotic solid lines results. And finally, for the case of Young modulus variation with average stiffness conservation, the value of the parameter B had a significant impact. For positive values of B, the frequencies differ little from the frequencies of a plate with constant Young modulus. For negative values of B, some of higher frequencies decrease rapidly with increasing epsilon. The conclusion I included at the last slide of my report. By means of the small change of plate parameters, thickness and stiffness, we can control the spectrum of free vibrations of the plate. That may be used to optimal design of a structure containing plate elements. The asymptotic formulas obtained in this work allow one to obtain good approximation for the eigenfrequencies of the plate vibration in the case of a small perturbation of the thickness or Young's modulus parameters. Moreover, the type of perturbation itself can be arbitrary character, in particular linear, quadratic, or which is encountered in application, exponential. At the same time, when creating a structure, it becomes possible to evaluate the change lower frequencies with a slight change in the geometry or properties of the plate material while maintaining the mass or medial stiffness of the plate. For plates with a fixed mass or medium stiffness, the perturbation according to the quadratic law is the most effective among the considered perturbation method. It is of interest to calculate the next term in the asymptotic formula for frequencies, which will allow, at least partially, to explain the nonlinear nature, the dependencies with the growth of epsilon. The necessary definition of the first amendment, the solution presents certain computation difficulties. Thank you for your attention.
Thank you for your interesting report. Dear colleagues, please ask your question. In this case, I have a question about system 2 and 3.
Sorry?
Equation system number 2 and 3.
One of the first pages.
Mm-hmm.
What about, say some words about the system. Where it is formulated.
It is formulated in the research articles by the
in reference.
Which added in my references at the end of my presentation.
Well, I can say a few words if you don't mind. Okay.
Okay.
Well, that's just classical equation of vibration of thin plates with variable parameters. The equation itself may be found in any manual, in any reference book, in any manual book. But here it's applied for specific type, for specific geometry of a plate, for circular plate, and all of these coefficients, which usually represented in some general form, were carefully calculated. So, well, partly it was done in some other papers by other authors, but in any way here, all of these terms were carefully collected, but for sure the equations for thin plates have been known for a century or more.
Thank you. Thank you. Thank you for your report.
Thank you.
The next report is on the movement of gyrostat under the action of potential and gyroscopic forces. This report presented by Kosov Alexander Semyonov Edward, but unfortunately there is information that the speaker will be absent. So we are taking a break, and in this case we have a few minutes to enjoy good music. See you in 15:45.
Летят невиданные сани, на облучке сидит судьба. Мы выбираем место сами, и начинается борьба. С утра судьбу мы погоняем, бросаем сани вверх и вниз. Ума к полудню набираем, и только думаем, думаем, держись! Ума к полудню набираем, и только думаем, думаем, держись. Идет уж вечер, мы устали, забытые юности дела. Неугомонными промчали, зачем борьба с судьбой была. Над нами крылья в темной ночи, ведут сыны и внуки бой. Когда по пять открыть нам очи, судьбы не выбрали б иной. Когда опять открыть нам очи, судьбы не выбрали б иной. С утра судьбу мы погоняем, бросаем сани вверх и вниз. Ума к полудню набираем, и только думаем, думаем, держись! Ума к полудню набираем, и только думаем, думаем, держись! когда ее ломают руки, терпит тонкая струна для тебя, рождая звуки. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Не могу в тени я быть, когда по небу солнце ходит, и по воле волн не плыть, тоже вовсе не подходит. Где же мне найти тебя и позабыть все прегрешения? Я скажу тогда, любя, ты одна, мое спасение. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться, мне не терпится в миру, коли любовь во мне искрится. Мне не терпится в миру, коли любовь во мне искрится.
безвозвратно играет ветер серебром. Душа болит, но как приятно опять приехать в мамин дом. Летят года, судьба играет, а домик маленький стоит. Никто там не вздыхает, и свет в окошках не горит. почет и слава от людей. Прости, родная, спи спокойно, уж внуки встали на крыло. У них в руках твоя икона, у них в руках твое тепло. Прости, родная, спи спокойно, уж внуки встали на крыло. У них в руках твоя икона, у них в руках твое тепло. Проходят годы безвозвратно, играет ветер серебром. Душа болит, но как приятно опять приехать в мамин дом. Душа болит, но как приятно опять приехать в мамин дом.
So the next report is resonant oscillation of a controlled reversible mechanical system in the vicinities of equilibrium. Will be represented by Ivan Barabanov. Okay, please, Ivan.
Dear colleagues, do you hear me?
Yes, yes, I do.
Yes, thank you. The title of the talk is Resonant Oscillations of a Controlled Reversible Mechanical System in the Vicinity of Equilibrium. The talk is presented by me, Ivan Barabanov, and the paper is prepared by me and my co-author, Valentin Tkhai, professor of Trapeznikov Institute of Control Sciences of Russian Academy of Sciences, Moscow. Here is a brief overview of the paper. We will discuss what is a reversible mechanical system, and later we discuss the conditions of resonant oscillations and a family of symmetric resonant oscillations. And the theorem represented will be illustrated by a simple example. When we consider a dynamical system, the Lyapunov theorem holds. That means that when the system admits a first integral, the system admits also a periodic motion in the vicinity of equilibrium. If the system is under small perturbation that with the frequency that coincides with one of the eigenfrequency, we can observe a resonant oscillation. The aim of this work is to establish conditions for a reversible mechanical system to have symmetric or unsymmetric oscillations, as well as to have a family, parametric family of symmetric oscillations. Now recall what is called reversible dynamical system. If there exists a non-degenerate linear transform G, such that the transformation x and t to gx and t yield the identical system, so we speak about reversible dynamical system. If the transform G is of the special form that is represented on the slide, then the system is called reversible mechanical system. In the reversible mechanical system, the phase space is divided into two parts. The first part U and the second part V, and the transform, symmetrical transform, is represented as UVT to U minus V minus T. And in this case, reversible mechanical system admits fixed set M. We will consider a reversible mechanical system that has an equilibrium in the 0 point, and suppose that the reversible mechanical system has linear approximation near the equilibrium. The linearized system can be written in the form 1. Matrices A and B are of the appropriate dimensions, and U and V satisfy the written conditions. According to the form of the reversible mechanical system, we can state that the system admits L minus n simple zero roots, and the other roots can be found from the equation in the form 2. For reversible mechanical system, we have a statement that is called Lyapunov-Bruno-Devanny theorem. This theorem is the analog of the Lyapunov center theorem. The statement of the Lyapunov-Bruno-Devanny theorem is represented on the slide. Now we will consider a reversible mechanical system that is under periodic control. Suppose that the system has L minus n 0 roots of the characteristic equation, and the remaining roots are purely imaginary. Then we can rewrite our reversible mechanical system in the form of 3, when we explicitly write the variables as he, x, and y. And the control, the right-hand side, is periodic. And suppose that the periodic control, the period of the control coincides with one of the frequency. So we will take only the part of the equation 3 that corresponds to the periodic control. And consider the system truncated to the terms of the third order. So we can obtain system in the form of 4. And for this equation, we can write explicitly the periodic solution. This periodic solution can be written in the form 5, 6, and 7, which are represented on these slides. So we obtain the following theorem. For a reversible mechanical system, we have the condition when the system has resonant periodic oscillations. In the general case, the oscillations are not symmetric. And now we pass to the case when L is not equal to N. In this case, we obtain the condition for a reversible mechanical system to have a family of symmetric oscillations. The appropriate statement is, let me omit the slides with the technical character and formulate the theorem. This theorem states that a reversible mechanical system under periodic controls admits L minus N family of periodic resonant oscillations when the characteristic equations has n pairs of purely imaginary roots. The stated theorem can be illustrated by a simple example of mathematical pendulum. The solutions of the pendulum on the phase plane are symmetric with respect to both abscissa and ordinate axis. So we can apply both theorem 2 and 3 such that we can obtain resonant symmetric oscillations with respect to x, symmetric resonant oscillation with respect to phase velocity, and as well we can obtain non-symmetric resonant oscillations. . Well, as a conclusion, we can say that we found conditions for a reversible mechanical system to have symmetric or unsymmetric resonant oscillations such that the response is of the order of k to the power 1/3. Thank you for your attention.
Thank you for your interesting report. Dear colleagues, please ask your question. So, in this case, I have a question. Can I say that it is about Hamiltonian system, everything, or not, or other system?
Exactly. Hamiltonian system are reversible mechanical system, of course.
Okay, it's very interesting for me. Thank you. Thank you. But no more question. Thank you for your report. The next report is algorithm for navigation mobile robots in a limited set of sensors. This report will be represented by Viktor Fyodorov. Victor.
Hello.
Hello, да. Please.
Hello, my name is Fedorov Victor, and the topics of my speech is algorithm for navigation mobile robot in a limited set of sensors. Today I want to tell you about problem of developing navigation system for autonomous robot movement in environment with obstacles. Currently, there are three most popular methods for solve this problem. First is potential field method, which based on building map with virtual forces. Second is most popular is building navigation system using localization and environmental mapping algorithms. You can see scheme of this method on the screen, and I want to tell that most popular algorithm of avoidance obstacles is DSTA on this moment. And third method is neural network method. In my opinion, building navigation system with using algorithms and potential field methods are the most effective at this moment. Now I want to tell you about new algorithm which based on these methods and allows autonomous motion without sensors such as gyroscope, accelerometer, and odometer. This new algorithm will call as modification of the DSTA algorithm. To implement the modification of algorithm DSTA, it is necessary to present the map of the environment in the form of grid map. All cells are divided into free cells and cells with obstacles. For effective work of this method, when constructing a trajectory in a deterministic environment, the A** algorithm is used. Modification of DSTA allows us to simplify the navigation system to one algorithm. When using it, there is no need to use localization algorithm and position sensor as gyroscope and accelerometer. DSTA algorithm search by graph algorithm based on A**. The result of this algorithm is a trajectory represented by a polyline on the grid map in various options in every cell robot can movement 4 or 8 direction. Let's move to modifying the D-star algorithm. At first, we need to scan environment and build grid map with start and target cells. As in D-star, for calculating the base trajectory, use a star algorithm with start point in the end of path and finish in the start. To reject position sensors, we need to enter some parameter for every cell on trajectory. First is m. M is the distance traveled from the target position of the path to the current point. Previous cell is next cell on the path because path building with starting the target point, and coordinates x and y. Consider the initial direction in which the robot in the starting point when the algorithm is launched, x sub 1 and y sub 1, where x and y in -1, 0 or 1. To find the direction from one point to the next along the trajectory, the following information is necessary. First is coordinates of the current point x and y, the direction of the robot at the current point, coordinates of the next point on the path. To move the robot, we need to know the following values. The direction dir, which equal -1 when backward movement, equal 0 when no forward movement, and equal 1 where forward movement. The direction of rotation turn, when turn equal -1 when right turn, 0 when no turn, and 1 when left turn. Also, we must know angle which between 0 and 19 degrees. Also, you can see equations of motion on the screen. Now we need to make two vectors in every cell. Vector A with the beginning at the current point and with the end in the coordinate corresponding to the direction of the robot at this point, and vector B with the beginning at the current point and the end at the next point on the trajectory. The angle between the vectors A and B is denoted by phi sub 0. We find this angle by the formula. By this angle, we can calculate variable dir and turn, as on screen. To improve efficiency of algorithm, we can use some potential fields method advantages. Target point wheel is an attractor that attracts the robot with constant force. You can see it on the screen. And obstacles, it's repellers. The repulsive force is described by the equation, which you also can see on the screen, where E is the number of the corresponding repeller and L sub E is the distance from the center of this investigated cell from the least to the center of the point of the Earth repeller. As a result, we can have result force, F result, which can be calculated by the formula on the slide. Draw a vector equal to the resulting one with the beginning at the intersection point of diagonals of the current cell if the distance from the center of the target cell to the end of this vector is less than the distance to its beginning, the movement to this point is acceptable if the conditions of the basic algorithm DSTA specified at the beginning of the step are fulfilled. This method allows us to build a navigation system that contains the advantages of the D-star algorithm and the potential fields method. We doesn't need a large set of sensors to use. Thank you for your attention.
Thank you. Thank you for your report. Dear colleagues, please ask your questions. Okay, in this case, I have a question. Victor, could you please say what is feedback information according to your research?
Can you repeat, please?
Feedback information. You can say you say about of sensors.
Mm-hmm. Yes.
In your topic. Feedback information.
No, for use this algorithm, which sensor we should use?
Yeah.
It's a distance sensor at first. It can be any types of sensor as laser, for example, any distance sensor from 1 to 4 sensor for best result. If we can use only one distance sensor, but it can have some trouble in motion. But if we have, for example, 4 distance sensor, it will good result.
As I know, you have an example, but in presentation it was not representation.
Yes, I have an example, but I don't think that it should be a presentation. I will add it next time.
Okay. Okay, thank you.
Thank you.
So we listened to all the reports of our session. See you in the next part. Which start at 14:60. Okay, see you soon.
Что такое ностальгия? Это боль и это крик, и разлука с дорогими, и
со всем, к чему привык. Ностальгия — это пламя, не зальют его года. Это раненая память об ушедших навсегда. Ностальгия — это значит очень сильная тоска, когда сердце горько плачет от любого пустяка. Ностальгия, как дорожка, очень трепетная нить, то, что больше невозможно ни вернуть, ни воскресить. Голову сжимает обруч, жизнь на медленном огне. Ностальгия — это горечь по потерянной стране, по утраченному детству, куда путь заказан вновь и не выдумано средства, чтобы оживить любовь. Ностальгия — это значит очень сильная тоска, когда сердце горько плачет от любого пустяка. Ностальгия, как дорожка, очень трепетная нить, в то, что больше невозможно ни вернуть, ни воскресить. Ностальгия — это значит очень сильная тоска, когда сердце горько плачет от любого пустяка. Ностальгия, как дорожка, очень трепетная нить, в то, что больше невозможно ни вернуть, ни воскресить. Ностальгия — это пламя, не зальют его года. Это раненая память о ушедших навсегда. Ностальгия, как дорожка, очень трепетная нить, в то, что больше невозможно ни вернуть, ни воскресить, в то, что больше невозможно ни вернуть, ни воскресить.
безвозвратно играет ветер серебром. Душа болит, но как приятно опять приехать в мамин дом. Летят года, судьба играет, а домик маленький стоит. Никто там не вздыхает, и свет в окошках не горит. Вот над могилою рябина, почет от леса и полей. К тебе приехали 3 сына, почет и слава от людей. Прости, родная, спи спокойно, уж внуки встали на крыло. У них в руках твоя икона, у них в руках твое тепло. Прости, родная, спи спокойно, уж внуки встали на крыло. У них в руках твоя икона, у них в руках твое тепло. Проходят годы безвозвратно, играет ветер серебром. Душа болит, но как приятно опять приехать в мамин дом. Душа болит, но как приятно опять приехать в мамин дом.
Первая ступенька, первые шаги. Каждый начинает от свои круги. Вот еще ступенька лестницы излом. Тут и поджидает нас первый перелом. Тут и поджидает нас первый перелом. На этаж поднялся, делай поворот. Видишь, как к вершинам движется народ, а ступени круче, каверзней злом.
Александр Юрьевич, вы меня слышите?
Я вас слышу. Здравствуйте.
Здравствуйте. Ну, я вот просто вначале пару слов скажу вводных, а потом вы поведете. Договорились?
Хорошо, сейчас только я у себя тут настрою все.
Ну, вы с Алексеем Викторовичем будете, так? Я тут правильно это понимаю?
Правильно.
Здравствуйте. Мы вас видим и слышим.
Здравствуйте.
Ну, тогда я в таком случае пока, если вопросов нет, я пока музыку тогда включу на всех.
Хорошо.
Сменяйте золото мое на мудрость старости глубокой. Бокал налей ты мне питье и дай мне хлеб рукой высокой, как ты давал ученикам в тумане древности столетий. Любви учил, любви к врагам. Прошло уж столько лихолетий. И ломтик хлеба, и вино, сокровищ всех ценней на свете. Любви в них столько нам дано, что хватит всем на всей планете. И ломтик хлеба, и вино, сокровищ всех ценней на свете. Любви в них столько нам дано, что хватит всем на всей планете. Сменяйте золото мое на мудрость старости глубокой. В бокал налей ты мне питье и дай мне хлеб рукой высокой. В бокал налей ты мне питье и дай мне хлеб рукой высокой. Стучат колеса неустанно, неутомимый электрон везет желающих к фонтанам. Приветствовать тебя, Самсон, герой, прославленный навеки в сказаниях Библии Святой. Зачем не упросили греки Геракла встретиться с тобой? Однажды в споре суетливом Самсон проспорил свой заклад. Не захотел быть он несчастливым, не захотел попасть и в ад. Со длинной челюстью он вышел на Торные в те дни пути, и 30 путников, я слышал, до дома не смогли дойти. А он, герой библейских песен, с лишенных жизни снял штаны и расплатился в споре честен. Видал ли Бог, кто с вышины? Стоишь вот теперь и пасть льву раздираешь, а он хрипит и бьет водой. Сковал тебя Господь, ты знаешь, чтобы мир не видел твой разбой. Герой прославленный навеки, в сказаниях Библии святой. Зачем мне его простили греки? Геракл встретится с тобой.
Dear colleagues, my name is Dmitry Shimanchuk. Sorry. Okay. My name is Dmitry Shimanchuk. I am moderator of this session. 5 speakers will be present their talks. All presentations are in English. Not more than 12 minutes are given for every presentation. 2 minutes before the end of this time, I will inform you about this. After that, there will be 3 minutes for questions. During the presentation, the audience will be mute. After the presentation, you can unmute yourself and ask a question. In addition, question can be asked in the chat and I will voice them, the same of the chat of YouTube, where the live broadcast goes. Меня зовут Дмитрий Шиманчук, я модератор этой секции. Будет представлено 5 докладов. Все доклады делаются на английском языке. На каждый доклад отводится не более 12 минут. За 2 минуты до окончания времени я сообщу об этом. На вопросы отводится 3 минуты. На время презентации я буду отключать микрофон всем зрителям. После презентации у вас появится возможность включить свой микрофон самостоятельно и задать вопрос. Кроме того, вопросы можно задавать в чате, я буду их озвучивать. Это же касается чата YouTube, где сейчас идет прямая трансляция. The session is chaired by Professor Alexander Alexandrov and Associate Professor Alexey Platonov. Please, Alexander Yurievich.
Thank you. Dear colleagues, hello, dear colleagues. I think we may to start our work, our session. And the first report is by Ivanov, Alferov, Korolev, Shimanchuk, study of the stability features of solutions of systems of differential equations. Please.
Alexander Yurievich, good day. Ladies and gentlemen, we present to your attention a report titled Study of the Stability of Solutions of System of Differential Equation. Isidor Pavlovich Natanson, in a monograph on the theory of functions of real variable briefly outlined the apparatus of derived numbers. A group of employees headed by Gennady Grigorievich Ivanov continued to develop this approach. The use of the apparatus of derived numbers allowed one to reduce the restrictions on the degree of smoothness of the right-hand side of the equation under consideration. This made it possible to expand the scope of the classical results. In particular, we have applied the apparatus of derived numbers to the study of estimating the number of periodic and almost periodic solutions of differential equation. Так, листай дальше. Так, excuse me. Геннадий Григорьевич Ivanov, candidate of physical and mathematical science, will report on the new results obtained in this direction. In the first section of the report, the partial derivatives number, we will outline the basic definitions of the concepts used in the report. And the second section, we will present the results obtained. Gennady Ivanov is the main developer of this method for studying the stability of ordinary differential equation. Consider a short list of Ivanov's work on this topic. Так, в конец выведи. Так. Ну вот, ага. Так. You see list works Ivanova. Так. One paper published in American Journal outlined Mathematics 2019. A new method to study solutions и так далее. Вот. This journal, Italian Journal Pure and Applied Mathematics, also printed in 2019. Так. Also, our paper published in book chapter, page 74. Что-то у меня мышка плохая говорит. Так, ага, ну все. Так, and the other journal. In second Так, in second pass, partial derivatives number, conditions and criteria for using partial and external derivatives are proposed. This makes it possible to study the behavior of a function of several variables without requiring its differentiability, but using only information about partial derivatives. They use the apparatus of external derivatives of numbers makes it possible to reduce restrictions on the degree of smoothness of manifolds when studying the question of integrability of the field of hyperplanes. Using the using the apparatus of partial and external derivatives of number, the study of the stability of solutions of a system of differential equation can be reduced to the study of the solvability of a system of equations of special type. Equations special type 4 and 5. 4 and 5. А где же она? Так, ну ладно. Excuse. The first section provides a definition of this concept, and the second section presents the result of applying the theory of multi-linear forms to the stability problem of a system of ordinary differential equations. Так, сейчас. Геннадий Иванов. Say word about this method this paper. Вот. You are ready?
Что ж, добрый день. Значит, суть того, что в докладе изложено, следующее. Мы все знаем определение...
English, please.
Excuse me, Mr. Ivanov speak in Russian.
I don't know English.
Так.
But official language is English. Official language of our conference.
Yeah. But because I suppose the Mr. Afsorov to do this report.
Так, our report is finished. What will be the question? this question will be answered by Gennady Grigorievich Ivanov.
Colleagues, please, any questions?
Пожалуйста, любые вопросы.
The reports is not.
Чего?
Is not.
Not это что? Репорт нет. Отчета нет.
But we haven't seen any results on stability of differential equation systems in your report. Не увидели мы результатов.
Результаты, значит так, результаты следующие. Приведен метод этих самых внешних, изложенных, строгое определение, что такое частные производные числа, что такое внешние производные числа. Ну, я, наверное, не буду рассказывать тогда, раз такое уже дело, а что это такое. Вот. Результаты следующие. Значит, мы показали, что этим методом можно доказать целый ряд теорем, но привели в качестве примера только две. Значит, первая – это теорема, которая дает условия устойчивости. Вторая теорема, которая дает условия равномерной асимптотической устойчивости нулевого решения рассматриваемой исходной системы. Значит, здесь результат сводится к нахождению разрешимости определенной системы уравнений, которые называли там номер 4 и 5. И эти уравнения должны обладать эти решения должны обладать определенными свойствами. Вот, например, теорема 1, она говорит, что если...
К сожалению, в докладе мы не увидели систем 4 и 5 и вот не увидели ни одной теоремы.
Почему тут? Не знаю, почему не увидели, не могу сказать вам, почему их нет. Я писал.
Так, ну это в статье, вот, особенно
доклад,
в американском журнале Mathematics.
Ну вот, суть там, первое уравнение, это как бы так, ну как вам тебе рассказать, вектор, вводится вектор А, n-мерный, умножается на функцию f, смотрится, чтобы он был меньше нуля. Второе, это условие, ну скажем так, похожее на теорему Фробениуса. То есть вводится понятие треформы, и требуется, чтобы вот это уравнение, эта треформа была тождественно равно нулю. Вот, собственно, из этих условий получаем, что ежели такое решение есть, и оно обладает определенными свойствами, то система у нас будет устойчива. Если там более жесткие условия наложить, то система будет асимптотически устойчива. То есть, и таким образом можно доказывать целый ряд теорем, и в частности, использовать этот метод, когда мы рассматриваем дифференциальные уравнения не просто так, а на каких-то дифференциальных многообразиях. И таким образом мы можем понижать степень гладкости рассматриваемых дифференциальных многообразий.
Ladies, we move on to the next report.
Спасибо.
The next report is by Alexandrov and Kovaleva, diagonal Riccati stability of a class of complex systems and applications. In this report, we consider a problem of diagonal Riccati stability for a special class of complex systems. We assume that the system describes interaction of subsystems of the second order, and this complex system admits a special structure of connections, and there are delay in connection connections between the subsystems. We will use standard notation. In particular, we consider Metzler matrices. Metzler matrix is a matrix with non-negative of diagonal entries, and we will consider non-negative matrices with all non-negative entries. Consider the linear differential equation system 1. Here A and B are constant matrices. Tau is constant non-negative delay. The system 1 is called diagonally Riccati stable if there exist two diagonal positive definite matrices lambda and omega such that the condition 2 is valid. It should be noted that inequality 2 is a matrix Riccati inequality, and the problem of diagonal Riccati stability is motivated by constructing diagonal Lyapunov-Krasovsky functional for system 1, and in the case where such a functional exists, we can guarantee that system 1 is exponentially stable for any non-negative delay. Consider a special case of the system 1, the case when this system is positive. Here the definition of positive system is presented, and it should be noted that system 1 is positive if and only if the matrix A is Metzler and the matrix B is non-negative. For this special case, it was proved a simple and effective criterion of diagonal Riccati stability. It is known that positive system 1 is diagonally Riccati stable if and only if the sum of A plus B is a Hurwitz matrix. Therefore, interesting problem is that of finding classes of systems of form 1, for which conditions of diagonal Riccati stability are equivalent to those for auxiliary positive systems. And for our auxiliary system, we can apply proposition 1. To solve this problem, the following proposition 2, can be useful. This proposition provides an approach to transform initial system to new system with transformed matrices. And in this report, we assume that we consider a complex system. We assume that the system 1 is a complex system describing interaction of the second order blocks. We assume that the matrix A is a block diagonal matrix with the blocks of the following form, and assume that we have special structure of connections between subsystems. As a result, we consider the system of a form free. Our goal is to determine conditions under which the problem of diagonal Riccati stability for free can be reduced to that one for an auxiliary positive system. First, it was proved that instead of original system free, we can consider system of the following form. We have new matrix A, and in this new matrix, of diagonal entries are non-negative. Hence, we have a new matrix A, which is Metzler matrix. And we have problem with the matrix B. To solve this problem, we introduce auxiliary matrix tilde B in the following form. And we consider the following assumption, assumption 1. According to proposition 2, we can guarantee that under assumption 1, the system 3 is diagonally Riccati stable if and only if the positive system of the following form possess the same property. And hence we have the problem of verification of assumption 1. For the verification of this assumption, the following theorem was proved. The theorem gives us necessary and sufficient conditions of fulfillment of assumption 1, and the proof of this theorem is constructive, and it provides us a special form of the matrices D tilde D and tilde E from assumption 1. And this constructive approach permits us to construct corresponding diagonal Lyapunov-Krasovsky functional for the original system free. Next, we will apply the theorem 1 to the system of a special form. We consider the system 6. This system also describes interaction of the blocks of the second order. And in this case, we have a more simple structure of connection. The structure of connection in the complex system is presented on this figure. In this case, the auxiliary matrix tilde B has the following form, and applying theorem 1, we arrive to the theorem 2. We have the following sufficient conditions under which the diagonal Riccati stability problem for system 6 is equivalent to the same problem for the auxiliary positive system, system 7. And we consider some applications of the proposed approaches two stability analyses of mechanical and biological systems. First, we consider system 8. We consider mechanical system with a positive parameter h at the velocity, at the dissipative forces, and applying the obtained approaches and applying idea of decomposition of mechanical systems, idea proposed by Zubov, we arrived at the following theorem. This theorem permits us to reduce the stability problem, delay-independent stability problem for the original system, mechanical system, to the stability problem, diagonal Riccati stability problem for auxiliary positive systems. And similar approach we can use for the following Lotka-Volterra system, the following biological models. And in this case, we also have corresponding theorem. This theorem permits us to reduce initial stability problem for the original system, system 9, to that for auxiliary positive system. It should be noted that in this case, the system 9 is nonlinear, but auxiliary positive system 7 is linear system, but conditions of stability of linear systems provides us sufficient conditions of stability for nonlinear systems, for nonlinear system. Here some references are presented, and thank you for your attention.
Dear colleagues, please ask your questions. It's very interesting, Alexander Yurievich, but we not have a time to discuss it because we need move on to the next report.
Yes, the next report is by Kirill Postnov, an estimation extension of domain of attraction for second order dynamic systems. Please. Please, Kirill Postnov.
Kirill, unmute your microphone.
Good evening. My name is Kirill Postnov. I'm going to present my study, an estimation extension of domain of attraction for second order dynamic systems. I ask you to excuse me for possible problems with the internet connections. Often, an estimate of the domain of attraction is only a small part of the real stability regions. For example, in the following figures, the estimate boundaries of dA are marked in black, and the domain of attraction are painted in red. Therefore, in my work, I have described the method for extension of estimation of domain of attraction for autonomous nonlinear dynamical systems defined on a plane. Consider an autonomous nonlinear dynamical system on a plane. Assume an implementation of the condition for existence and uniqueness of the solution at any point of the plane, and an asymptotic stability of the resolution. Let E be an estimation of domain of attraction obtained by any methods, for example, Zubov methods. My method is based on the idea that a small domain E star can be added to the existing estimate of domain of attraction E. These slides show sufficient condition for union of set E and E star be an estimation of domain of attraction. The first conditions, trajectories of system, intersect the arc G bar from outside to inside, while T goes to infinity. The second conditions, there are no special points in the domain E star. To use this proposition, describe a way of constructing the domain E star, satisfying its conditions. Consider an autonomous nonlinear dynamical system on a plane. System 1. Let E be an estimation of domain of attraction obtained by Zubov method. Function V of x and y satisfies this condition. This slide describes the computational algorithm for extension of estimate of dA. This algorithm consists of two main parts. The first part is items from 1 to 3. In this part, we prepare required data for using algorithm. The second part is step 4 and step 5. In this part, we construct a domain E star from proposition 1. I'm going to illustrate and explain this algorithm with via a simple example. We consider the autonomous dynamical system from presentation beginning. In figure, the estimate boundary of domain of attraction V is marked in black, and the domain of attraction is painted red. Step 1. Choose the point A and B on the boundary of the domain of attraction estimate. Connect the point A and B by the chord and mark the point C with coordinates. Step 2. The distance between the point A and C denoted by rho over score. The distance between the point C and the closest point on the boundary E denoted by rho underscore. Calculate value rho underscore and rho over score. Suppose the conditions rho underscore is smaller than rho over score is satisfied. Otherwise, it is necessary to choose other points A and B. Step 3. Consider the semicircles family. This figure shows several semicircles for 5 different value rho. 1, 2, 3, 4, and 5. The function R of x1, x and y is equal rho. Show its slide. Calculate the time derivative of the function R evaluated along the solution of system 2. Construct the set M from the following condition. The first multiplier in the left-hand side of equation is always positive. Therefore, the set M takes the following form. Now we should calculate rho sub 0 with shown constraints. We gain rho sub 0 is 1/4. The domain formed by the estimate boundary of domain of attraction V and semicircles R of X and Y is equal 1/2 will be E star from proposition. In figure, this domain is painted gray. The extended estimates of dA is shown in figure. That's all. Thank you for your attention.
Thank you for your report. Colleagues, please, any questions? Please.
You describe a one-step procedure in your work. Is it possible to propose a multi-step process that seeks to precisely estimate the region of attraction? Можно ли это как-то продолжить, чтобы получить точную оценку?
Yes, we can repeat these algorithms another, but we don't explicit estimate because we cannot all domain of attraction, but we goes to domain with repeat algorithm. В общем, точную оценку, точную область мы таким образом не получим, но сможем к ней приближаться, повторяя снова и снова алгоритм.
Вот эти точки на point you choose arbitrary. Вот A, B, you arbitrary choose. То есть наугад выбираете. То есть есть какие-то рекомендации, как их лучше выбрать? Sorry for my English.
Yes, it random points.
Thank you.
Но дело в том, что если вы их выберете, скажем, на оси X, то ничего хорошего, наверное, не получится.
It's you are right, but in my paper I describe более подробно this algorithm, and one from condition the chart from A to B don't contain special points and points where time derivative along time derivative of function R evaluated along the solution of system is not equal 0. That's point A and B lays on axis X. Не подходит. And more than this condition is not true in this case.
Yes, thank you. The next report is by Alexander Kirillov, Alexander Sazonov, Economic Evolution with Structural Variations. Please.
Hello, dear colleagues. The title of my presentation is Economic Evolution with Structural Variations. My name is Sazonov Alexander. My co-author is Alexander Nikolaevich Kirillov. I begin with some history. At the beginning of the 20th century, the Austrian economist Joseph Schumpeter proposed the theory of the endogenous economic evolution, based on the two processes, the innovations, that is creation of new technologies, and imitations, the borrowing of technologies. The mathematical formalization of this theory was developed by Russian scientists Poltorovich, Henkin, and Shunanin. And they constructed a variety of the mathematical models of the Schumpeterian dynamics, in which the economic systems, for example, sectors, in which the firms are ordered by efficiency levels, are considered. Here are the main assumptions for these models. So, this is the capacity dynamics model described in the work by Henkin and Shunanin. In this framework, efficiency levels differ in the profit per time unit per capacity unit. The dynamics of the capacities is described by the following differential equations. As a result, the distribution of the capacities is obtained. But this model has a weakness that the growth of the capacities is unbounded. This is incorrect from the economic perspective. So, the main idea to eliminate this problem is using the following equations. Here C is the integrated sector capital and V is the economic niche volume. It is a limit capital value for which the growth rate is so low that we can say that there is no capital growth. Here is our model of the sector capital distribution dynamics. We consider a finite number of efficiency levels, and the dynamics of the capital is described by the following system of the differential equations. In this case, the economic niche is shared, so the levels compete. The right-hand sides of the equations contain two addends. The first addend describes the capital growth due to the production at the actual level, and the second one due to investments from the previous level. The functions phi sub I are continuously differentiable. This is the main theorem of their research. If this condition holds, then the equilibrium P is globally stable. The condition of the theorem means from the economic perspective that the contribution of the production at the level I to the capital growth at this level is not arbitrarily small in comparison with the contribution of the investments from the previous level. So we can say that this condition is natural. Note that the matrix of the partial derivatives has at the equilibrium P the eigenvalues equal to 0, which makes the problem of global stability more complicated. The global stability of the equilibrium means the stagnation from the economic perspective, which is extremely unfavorable situation. According to Schumpeter's concept of the creative destruction, when the evolutionary changes are impossible, so this is stagnation, the revolutionary ones are necessary. We propose the emergence of a new highest efficiency level as a revolutionary change. According to our scenario, the new level emerges when the positive half trajectory intersect the neighborhood of some delta neighborhood, intersect the boundary of some delta neighborhood of the equilibrium. It certainly happens because of the global stability. Delta is a preassigned constant and it depends on the sector. Besides, we propose the scenario of the vanishing of the lowest level 1. It is shown that the capital at the first level tends to 0 as t tends to infinity. So when this capital is sufficiently small, it may be neglected and considered as vanishes. The first level vanishes, then the capital at this level reaches a value epsilon, where epsilon is a sufficiently small preassigned constant. So we have the system with the variable dimension. The dynamics of this system is the following. Because of the global stability of the equilibrium, the capital at the highest level approaches the value of the economic niche volume, while the capitals at other levels tend to 0. But at some time moment, the new highest level emerges, and after that, the capital transfers to this new level, and the capital at the previous highest level tends to 0. Herewith, the low levels are vanishing step by step. So the capital moves to the permanently emerging new highest levels with vanishing of the low levels. We can say that the capital concentrates at high levels, which numbers permanently increase. Let n of t is the number of levels at the moment t, and low of t is the number of the lowest level existing in the economic system. Denoted by gamma of t, the binary infinite dimensional vector. Each component gamma sub I of t equals to 1 if the level with the number e presents in the economic system, and equals to 0 otherwise. It is clear that the dynamics of the discrete system presented by gamma is described by parameters low and n and depends on the parameters epsilon and delta. Here we have an interesting result if epsilon divided by delta is greater than 1. Then for any initial values, the system will switch between two states, one efficiency level and two efficiency levels. The economic interpretation can be the following. The sector is very mature, and any new technology, any innovation leads to vanishing of the low level because it cannot compete with the new high level. So I've finished my report. Thank you for your attention.
Thank you for your report. Dear colleagues, please, any questions? There are no questions.
You consider some structural variation, some switching in economic system. Is this switching a control method or a control goal?
It's not a control method.
This is goal. We must to change level with economic method.
Yes, I understand. I explain. Boltrovich and Henkin consider the system with infinite number of efficiency levels, and they obtained the wave of the distribution. So we consider the system with a finite number of levels. And we have to consider this structural variations for comparison with their results. So, and the global stability means the stagnation, and we must avoid this situation by the structural variations.
Thank you.
Thank you. The next report is by
Alexandrovich, I'm sorry, but we need wait a few minutes because each report has its own time. I'm sorry.
Yes. We have about 6 minutes.
Yeah.
We may discuss some previous reports if there are some questions.
I have a question for your reports, but about mechanical models. What is the real mechanical model described by system 3, 6, 8? It's interesting for everything.
We can consider a model of a form 8. In this model, we have corresponding coordinates. We have coordinates with even indices and coordinates with odd indices. And for this structure of the system, we can consider coordinates with odd indices as coordinates of binding bodies and coordinates with even indices as coordinates of carrying bodies. And structure of connections provide us a situation when we have interaction between carrying bodies, between coordinates with even indices, and the coordinates of carried bodies are interact only with bearing. Bearing bodies interacts only with carrying bodies. То есть мы можем вот замкнутую такую цепочку построить из несущих тел, а на каждом несущем теле еще имеется вот несомое тело, которое с несущим только взаимодействует. А сами несущие, они еще между собой взаимодействуют. То есть именно вот интерпретация вот такой структуры связей.
Thank you. And your students are investigate these models yet?
My students investigate some variations of such models. We have some several results on the interaction of web blocks of a second order with application to mechanical systems, to multi-agent systems. In particular, we consider the problem of equidistant deployment of agents on a segment and some other applications.
Thank you. Okay, I think that we
can continue.
Yes.
The last report is by Alexey Platonov on the stability of nonlinear mechanical systems with time-varying discontinuous coefficients. Please.
Dear colleagues, let me represent my report. In this paper, I consider a class of mechanical systems with nonlinear false fields. I assume that system is under influence of dissipative, gyroscopic, and potential forces. I suppose that there is a non-stationary coefficient at potential forces. In the case where this coefficient is piecewise continuous and piecewise monotonous on any finite time interval is investigated. I study the situation where this coefficient can be unbounded. Stability conditions for such class of mechanical systems are obtained. Notice that there are many works where the stability problem was investigated for nonlinear mechanical systems with non-stationary parameter at potential forces. However, some restrictive assumptions were used in these works. In particular, it was assumed that the derivative of the parameter tends to 0, or that the parameter has a positive average value, or the parameter is described by a monotonous function. In the present paper, I try to work in this assumption. If non-stationary coefficients of the system are discontinuous, then it can be considered as a switched system with generally infinite numbers of operating modes. Breaks of the coefficients can be caused by sudden changes in external condition or by a change in the control design. For such systems, the method of multiple Lyapunov functions was developed as effective method of stability analysis. Let me consider these mechanical systems. This Q and Q with dot are vector of coordinates and velocities. T quadratic form described as the kinetic energy of system. It satisfies standard assumption. The terms in right hand describe forces, fields in the system, dissipative systems, gyroscopic systems, and potential forces. Dissipative forces, gyroscopic forces, and potential forces. And I assume that there is non-stationary coefficient at potential forces. I suppose that function R and P are described by homogeneous functions of corresponding orders, nu, mu. The aim of the paper is to analyze the stability of the equilibrium position of the zero equilibrium position of the system. This work continues my previous research. Previously, I have studied the situation where the non-station parameter is continuous and bounded at above, but it can be arbitrarily closer to zero. In the present paper, I assume that parameter is separated from zero, but I assume that it can be discontinuous and unbounded at above. Notice that system 1 with unbounded parameter h also was investigated early, but the assumptions that function h is positive, continuously differentiable, monotonically increasing, and it tends to plus infinity were used. In the present paper, I use more general assumption. I don't assume that this parameter is monotonic and it can describe a oscillation, non-monotonic. Let tau eta be the sequence of time instants where the function h has a break or changes the character of monotony. I construct multiple Lyapunov function which consist of two partial Lyapunov function v1 and v sub 1 and v sub second. Functions v sub 1 I use on the interval where parameter increases. Function v sub 2 I use on interval where this parameter decreases. I try to construct some differential equations for this Lyapunov function for at interval of continuity. Since Lyapunov function is discontinuous, I must to estimate the change of Lyapunov function at breakpoints. This parameter k, l, rho are defined through parameter systems. In result, I have some estimators which allow to me obtain stability conditions. I construct some non-stationary function by this formulas complex. And if this function tends to infinity, then equilibrium position considered is asymptotically stable. I use assumption 1 that function h is bounded at below by positive constant, and I use some estimators on derivatives on interval of continuity. Let me consider some example. Let parameter is between two function, power function. This function, I assume that this function increases on intervals with such intervals and decreases on such intervals. And if the length of intervals of increasing tends to infinity, then system 1 has equilibrium position which will be asymptotically stability with respect to Q for any conditions on orders of homogeneity of present forces, for any mu, for any nu. If addition inequality valid, then we have asymptotically stability with respect to all variables. In the second part of my paper, I consider the method of single Lyapunov function, only function v1, v sub 1, without v2. But by using this function in differential inequality for this function, I obtain additional linear term I obtain this differential inequality, but on the intervals where parameter h decreasing arises some additional term arises in these differential equations. So I have comparison equation of Bernoulli type. Also, I use some estimators and breakpoints for Lyapunov function and have the result. I construct auxiliary function, and if this function tends to infinity, then it guarantees the asymptotic stability of considered equilibrium position. These functions depend on parameter systems. Parameter k, sigma, g, j are defined through parameter systems. In partials where function h be continuous, we have simple condition of stability. If this tendency is valid, then equilibrium position is asymptotically stable. Consider this example. Let parameter I h of t is between two linear functions in sector. Then I can obtain simple condition of equilibrium of asymptotic stability for equilibrium position. This condition. It should be noted that here I don't use any assumption about length of monotonicity interval of function h of t. Under this condition, I guarantee asymptotic stability for any function h satisfies these conditions, and assumption 1. In the second approach, I use a more conservative assumption on derivative, but I use a less conservative assumption on lengths of monotonicity intervals. Therefore, two approaches considered have some advantages, and it can be considered in all other situations. That's all. Thank you very much for attention.
Thank you for your report. Any questions, please? Colleagues, are some questions or not?
No questions in the chat.
No questions. In this case, we can finish our work. Thank you for your attention. Thank you for interesting reports.